All right, now that we've got this whole notion of implicit differentiation down, the next step is to apply this to figure out the derivatives of inverse trigonometric functions. And what we know so far is we know the derivatives of sine, cosine, tangent, cosecant, secant, cotangent. We know the derivatives of our basic trig functions. The inverse functions, what we're going to do is we're going to just take the derivatives of our normal trig functions. Now, let's think back to past experiences where we know that y equals sine inverse of x or y is arcsine of x. That means that we've got sine of y equals x. Inverse or arcsine, now those two terms are interchangeable. For the most part, I will be writing arcsine just to avoid any ambiguity with that negative one as an exponent. That means sine inverse, not the reciprocal, not sine to the negative 1, not cosecant. It means inverse sine, saying it takes a ratio and gives us an angle as a result. Now, thinking back to the past, in order to make this a function, in order to make the inverse a function, we restrict our domain. That makes this passes the horizontal line test. Over this restricted domain, we have a one-to-one function. Now, y equals arcsine of x, we're going to apply implicit differentiation strategies. We're going to first rewrite this so we've got sine of y equals x. Now, we're going to apply our derivative, d dx, onto this equation, sine of y equals x. That gives us now sine, the derivative of sine is cosine of y multiplied by dy dx. Now, just to avoid any ambiguity, I've got cosine of y multiplied by dy dx equals the derivative of x is just 1. That's not too bad. Solving for dy dx equals 1 over the cosine of y. Now, that's in terms of y still. We want to get this in terms of x. So we're going to make this substitution where we know that y is equal to the arcsine of x. So our derivative is 1 over the cosine of arcsine of y. We're going to perform a little bit of trigonometric magic on this. Remember, back to pre-calculus experiences, we have this statement, sine of y equals x. Well, sine of some angle is the ratio of the opposite side to the hypotenuse in a triangle. So what that gives us is we have a triangle where our angle is y, our opposite side is x, and our hypotenuse would be 1. That would give us sine of y equals x. Arcsine of y, this tells us arcsine of x tells us that we have some angle y such that the opposite to hypotenuse is x to 1. We want the cosine of that angle y. So we want cosine adjacent over hypotenuse. Pythagorean theorem tells us this side would be 1 subtract x squared. Cosine of the angle y is then equal to square root of 1 minus x squared. Oh, actually, look at that. Cosine of y is square root of 1 minus x squared. So our derivative, dy dx, is equal to 1 over the square root of 1 minus x squared. That is the derivative of arcsine. Let's take another one. Let's find the derivative of arctangent of x. I'm going to apply the same strategy where this is equivalent to saying the tangent of y is equal to x. Applying our implicit differentiation, I'm going to apply the differential operator d dx on tan y equals x. Derivative of tangent is secant squared. So we have secant squared of y multiplied by chain rule, derivative of the inside, dy dx, is equal to the derivative of x, which is 1. And so we get dy dx is equal to 1 over secant squared of y. Now we have this tangent of y is equal to x. Tan y is equal to x. Tangent, we remember, tangent of some angle is opposite over adjacent. So we've got opposite over adjacent. I can rewrite that as being x over 1 in this case. Secant, as we recall, is adjacent, nope, that's a lie, hypotenuse over adjacent, the reciprocal of cosine. So let's think about this in a triangle. We have tangent of y is x, so we have some angle y in our right triangle for which the opposite is x, the adjacent is 1. Secant is the hypotenuse over adjacent, so the hypotenuse in this case by the Pythagorean theorem is going to be x squared plus 1, the square root of that. So secant is going to be hypotenuse over adjacent, we're going going to get that to be square root of x squared plus 1. Substituting that into our statement, where our derivative of arctan is 1 over secant squared of y, well, I'm going to substitute that in, square it. That gives us 1 over x squared plus 1. And so we have the derivative, dx, of arctan x is equal to 1 over x squared plus 1. Let's apply these with a few examples. Differentiate y equals 1 over arcsine of x. I could use the quotient rule here. I'm going to rewrite this as being y equals arcsine -1, meaning reciprocal, and I'm going to apply the chain rule here. So I'm taking the derivative. It's going to get us dy dx equals derivative of the outside will be -1. Keep us inside the same arcsine of x, subtract 1 from the exponent of -2, multiplied by the derivative of the inside. We have 1 over square root 1 minus x squared. That is the derivative of arcsine. Simplifying, we have dy dx is equal to -1 over square root 1 minus x squared multiplied by arcsine x squared. Notice that I am putting my exponents outside of parentheses on the end. There is no arcsine squared. We do not write it that way. I'm going to close my parentheses as such. Let's take x arctan square root of x. So first off, we have the product rule. Square root of x is the argument of arctan, so that's going to require the chain rule there. So let's apply our derivative d dx on x multiplied by arctan square root of x. Product rule, derivative of the first derivative of x is 1 multiplied by the second arctan square root of x. Add to that the derivative of the first, that's a lie, derivative, keep the first the same, multiplied by the derivative of the second, derivative of arctan, it's going to be 1 over the argument, x squared plus 1, because the derivative of arctan is 1 over x squared, where x is our argument, so the square root of x squared plus 1. Now, chain rule, since we had the square root of x inside arctan, I'm going to multiply by the derivative of the square root of x. So multiplied by 1 over 2 square root x. Meaning, we have our derivative is arctan root x plus x over 2 root x multiplied by x squared plus 1. That's a lie, not x squared plus 1, because the square root squared is just x plus 1. I notice that x over the square root of x, that's like x to the 1, x to the 1/2. We have arctan square root of x plus square root of x over 2x plus 2. There we go. Let's do one more derivative, this time arcsecant. So that's going to be the equivalent of secant y equals x. If we apply our derivative d dx onto that, we're going to have secant y tan y multiplied by dy dx. Secant of the argument, tangent of the argument being y in this case, that's the derivative, multiplied by the derivative of the inside, multiplied by dy dx, equals the derivative of x, 1. So we have dy dx equals 1 divided by secant y tan y. Or, in other words, we have dy dx is equal to 1 over, well, secant y, let's go back to our triangle. If we have secant y equals x, that's going to give us a right triangle. Secant is a hypotenuse over adjacent, so we've got hypotenuse is 1, hypotenuse is x, adjacent is 1. The opposite side will be the square root of x squared minus 1. So the tangent of y is going to be square root x squared minus 1. The secant is going to be x. Now, because this is a side of a triangle, it is always going to be positive. So I'm going to denote this with the absolute value. It is the absolute value because it is the side of a triangle. So secant line, taking and substituting these into our statement, this is going to be the absolute value of x multiplied by the square root of x squared subtract 1. There is our derivative for arcsecant. Pulling everything together, we have 6 different functions. What I want you to see is the similarities between these. We have arcsine that we derived together. Arccosine is the same, except we would have that negative. And it goes back to taking, if we had d dx of cosine of y, it would give us negative sine of y. And the same rules apply, but there's just that extra negative now. Arcsecant, we just saw, we've got the absolute value, square root x squared minus 1. Arccosecant is the reciprocal of cosecant being reciprocal of sine. But what I notice is cosecant has the same, but it's negative. Arctangent, as we derived, arccotangent, negative. The way I remember, just like the parent functions, cosine, cosecant, cotangent, whenever we have that c, change the sign, makes them all negative. These are additional rules that you should remember at this point. We're going to keep on playing along. Have fun.